is time for the big activity. I was going to have you guys do. You get to do this on your own now. Basically, what I'm going to show you at the end of the slide is, on the very last slide, is several descriptions of motion and several motion graphs. And your job is to take each sentence and each line on the graph and decide which pile it goes into. Is this a situation where there are no net forces, or is this a situation where there are net forces? Okay? So, for example, here, one of these is a train moves down a straightaway on the tracks at 35 miles per hour. Are there net forces or not? There's also a few different lines on the graph. So make sure you pause the video and take a few minutes to sort all of these. Once you have them sorted into piles, and you can do that just by writing down lists in your notes, you can hit play again. Okay, I'm going to assume you've done the work of sorting these into piles because that's how you're going to learn things the best. Okay? And let's talk through these. So, we'll start with the descriptions. The first one, we have a train moves down a straightaway on the tracks at 35 miles per hour. And if we were to think about the motion diagram for this, it would look like this. We've got pretty much constant motion, same distances in between for each time, and importantly, we're moving in the same direction as well. Both of these things have to be true, but if they are, it means the motion is constant, and that means no net forces. So this is an example of no net forces. Okay. Number two, a car turns a sharp corner at 20 miles per hour. Okay, 20 miles per hour, that's a constant speed. They keep that speed. So you might be tempted to think that means there's no acceleration, but they're turning a corner. That means their direction changes. Velocity is both parts, how fast you go and what direction. If either of those change, it means you accelerated. So number two here is definitely accelerating, and that means there must be a net force. Okay. Turns out the net force that helps your car turn a corner is friction. So thank you, friction. Again, you know that if you've ever tried to take a corner and it's like really rainy and oily and slick on the road, you might almost spin out, okay? And so we know it's the friction that helps us stay in that corner. Okay, number three, a skydiver uses a parachute to float to Earth at 53 miles per hour. Okay? So they are going at constant speed. And if they're floating to Earth, we can kind of assume they're coming straight down. That would be an example of no net forces, okay? Constant motion. Number four, you can push on a chair that has wheels. Okay, I'll go push on a chair that has wheels. I can do it that way. Or I can do it this way. There are lots of different ways you can push on a chair that has wheels, and so this one is a little bit more, could go one way, could go another, depending on what you thought was happening. So if, in the first example, I was pushing it in a way to balance the friction, and so that was no net force. Or I could be pushing it and let go, and then only friction acts on it, and it slows down. That's a net force that's not zero. Or the other thing I can do is push harder, and then I actually accelerate. So I start slow, then I get faster and faster. That would also be no net force. So let's assume it's one of those scenarios where there is a net force, excuse me. So either there's a lot of friction or there's a lot of push, but either way, they're not balanced. Okay, what about the graphs? So A, here, these are position versus time. So we have to think about what that means in terms of their velocity, and then what that means in terms of their acceleration. So A here is a straight line that comes down and crosses the axis? Constant motion or changing motion? That's the question. So as I come here in my straight line, I'm covering the same distance every same amount of time. That means that I'm going the same speed. Now the question is, have I changed direction? Right? Because I cross the axis. I go from positive positions to negative positions. Does that mean I turn around? So here's what that could look like. So let's say that this marker here, the center of this, is my 0 point. Okay? Positive is this way, negative is that way. Okay? To make this motion, I could be over here. So I'm at a large positive number, I'm far away from the marker, and then I'm going to move towards it at a constant rate, and then I pass it at a constant rate, and now I'm in the negative numbers. Did I change direction? No. So A here is an example of constant motion, no acceleration, no net force. What about B? B, we start here positive and we go up, but again, our slope does not change, our speed does not change, and this time it's even easier, they're all positive numbers, so our direction definitely didn't change. And the other way to think about that is, we keep getting further and further away. To change direction, you would have to literally turn around and start getting closer and closer. And then lastly, C is a curved line that comes down. And a curved line in position means that our slope is changing value in time. So up here, it's really shallow, so it's slow. Here, we get steeper and steeper. So our object is getting faster and faster. It's accelerating. In fact, that looks a lot like what happens when you drop something. Okay? And we know we accelerate in that case. All right, so those are putting them into piles. The next thing to do is to look at your no net force pile. Okay? So let's focus on, I would say, let's just do line B, and let's do number 3, the skydiver. Okay. So for those, what happens? There was no net force. What happens if a force is suddenly applied in the same direction as motion? You would get a different effect if the force were applied in a different direction. This is just one possibility. Okay. So the question is, for these where no net force have been acting, what happens if the force is applied? So you'll want to pause this again. You will draw on the graphs what the new motion looks like, and then you can write part of a sentence to explain what would happen to the skydiver. Okay, so do this for line B and the skydiver. Okay, now let's think about this. So, let's do the skydiver first. Okay, our skydiver is coming down nice and slowly, and then maybe right before they land, so this is safe, they're like the line snaps or something catastrophic happens, and they no longer have a parachute. Oh no. So now you have a net force because the parachute is catching air, okay, and it's balancing with the gravity that pulls you down. So now we don't have that. Oh no, we just have gravity pulling us down. What do you think would happen? They get faster, okay? So if their direction before looked like this, so each of these vectors is the same length because they're going at a constant 53 miles per hour. Once it snaps, these are going to get faster. Because now there's the force pushing in that direction, it accelerates you in that direction. Your acceleration, A, and your force, your net force, are going to be in the same direction. So if we have a net force that is down, we now have a net acceleration that is down. What about line B? So for the line, this is again position and time. Started up here, moving up that way. Okay? So, draw a little bit easier. So we have some constant motion here, And once again, it's moving in this positive direction. We have an acceleration in the positive direction because our net force is in the positive direction. That means we will speed up. The way we see that on a graph is the slope gets steeper. So this will turn into a very steep line. So it'll go from relatively flat to very steep. We got faster. Okay? Now I want you to do this again. Okay? And again, at least just for a few of these where there is a net force. And the question is, what would it look like? What would the behavior be if the net force stops being applied? So let's do this for line C and the car turning the sharp corner. Okay? So for those two scenarios, the car with the corner and line C, draw or write what would happen once that net force stops being applied. Okay, let's think about this. Let's do the car going around the corner first. Gotta kind of draw this. So here is the corner of the road. Here is my car, and they are moving this way. And when the force, like the friction, stops being applied, because maybe, again, they made a wet spot or slip spot on the road, okay? Then whatever their velocity vector is, that is now their new velocity vector. Off the road they go, okay? In the direction they've been heading, at the speed they've been going. Okay, what about line C? So we were here, and it looked like this. So again, it was falling, it started flat, and it got steeper. And also we're going to turn off the force that applies this. And so again, whatever slope we have here, that represents the speed that we have. And so that is going to be the slope that we keep. So we're not going to get any steeper or any shallower, we're going to keep the steepness we have. That's how you show that the velocity doesn't change.